So what we're doing today is we're continuing on with factoring. But the ones that we're covering today and possibly tomorrow are what I consider kind of some of the special cases. We've covered one of these, well, there was one of the ones on the homework that would fall under one of the special cases, and that would be this one here. And what they would consider this to be is a sum or different, or a perfect square trinomial. Essentially what they're saying is that this here will eventually end up factoring as the form of a plus b squared is equal to a squared plus 2ab plus b squared, or in the case of a minus b squared is equal to a squared minus 2ab plus b squared. And it is possible to use this formula to be able to go from one to the other, either going from squared form to factored form or from expanding or condensing these two here, going from one to the other. I find that trying to use the formula and work that out, you end up spending about the same amount of time as if you just factor the thing already. So whenever we come across something like this here, really, we can look for greatest common factors first. Well, between 4x squared, negative 4x, and 1, there's not really a greatest common factor. So we'll have two sets of parentheses with 3 spaces. And then we'll find the signs. Since the third term is positive, the signs are the same, and they match the sign of the middle term. Minus and minus. Now we need to find the factors of the first and third term. Well, the factors of 4x squared, well, we do know that we will have x and x. Now the factors of 4 are 2 and 2. Now the factors of the third term, well, 1 is going to be 1 and 1. Anytime we have one set of factors, I'll just go on and throw them in because they're a little bit easier to work with. Now, do we want to try 1 and 4 first, or 2 and 2? 2 and 2. And we did say that these are kind of special cases, so most likely 2 and 2 is going to work. And if we check this here, 2x times negative 1 is negative 2x. Negative 1 times 2x is negative 2x, which gives us negative 4x. Now, the reason I do classify this as kind of being a special case is because both sets of parentheses are the exact same thing. So realistically, I could actually rewrite this as 2x minus 1 squared. So either one of these is the correct factored form. And that's it. That's all we have to do for this here. Any questions on this here? (16b squared minus 40b plus 25). Okay. Is there a greatest common factor between all 3 terms? Well, no. Because 16 and 40, yes, but the 25, not so much. So we'll have 2 sets of parentheses with 3 spaces. Since the 25 is positive, the signs are the same, and they match the sign of the middle term, which works out to be negative and negative. Now we need to find the factors of the first and third term. Well, we do know that we will have b and b, because we have to split those apart like that. Now we need to find the factors of 16. 4 and 4. Which one do we want to use? 2 and 8. And with 25, 5 and we can use 5 and 5. And if we check this here, 4b times negative 5 is negative 20b. Negative 5 times 4b is negative 20b, which gives us negative 40b, exactly what we wanted. So these here are the correct factors, or we could say 4b minus 5 squared. Either one works just fine. Any questions on this here? And it would work out the exact same if the middle term was positive. It wouldn't make a big difference. We would do the exact same steps, except instead of having subtraction in the middle, we would have addition. So any questions on number 14? So let's look at this next one here. N squared minus 25. Now we could treat this the exact same as what we've been doing, as looking for greatest common factors first, and well, here there's not going to be one. Now it technically doesn't have a third term, but we also don't have a middle term either. Yes. Since it is negative, the signs would be opposite. Now the factors of the first term are n and n. Now if we look at the factors of 25, well, we would have 1 and 25 and 5 and 5. Which one would we want to use? 5 and 5. And if we check this here, 5 times n times negative 5 is negative 5n. 5 times n is plus 5n, which gives us, and since we don't have a middle term, that's what we want. So this here would be the correct set of factors. Questions on this here? Now the other way that we can look at this is by the definition. A squared minus b squared is the difference of perfect squares, is equal to a minus b times a plus b. And we could write that in either order. We could actually have said a plus b times a minus b. Either one works. So if we have a difference of perfect squares, our two here are perfect squares, can be written in the form of a number times itself or a term times itself, then this here is going to be the difference of perfect squares. Or essentially, can I take the square root of both terms? So could we take the square root of 16n squared? And what would the square root of 16n squared be? 4n. And what would the square root of 9 be? 3. So we can take the square root of both terms, yes? Or essentially what we're saying is that both of those terms, 16n squared and 9, are perfect squares, and they are being subtracted. So this would be the difference of perfect squares. Which means this here would factor to 4n plus 3 times 4n minus 3. And we could have it in either order. So we could have written it as 4n minus 3 times 4n plus 3. It would be the exact same thing. And we have it factored. And that's it. Now this here, I use the formula for it because it actually is faster than if we actually tried to factor it out, like on the last one. Any questions on this here? Because everything we've done so far has not been new. Would y'all agree with that? Because we did this last semester, we did it with our quadratics. So what would this one here be? 2m minus 5 times 2m plus 5. And that would be it. Because 4m squared is 2m times 2m. 25 is 5 times 5. They are the difference of perfect squares. So we get this here. And I think the difference of perfect squares are some of the ones that y'all like factoring out of any of them, because they're easier to work with. Yes? We're ready for the next one. This is technically new-ish, but let's look at this here. A to the fourth minus 9. Is a to the fourth a perfect square? Because a to the fourth, I could rewrite it as a squared times a squared, yes? Because whenever we multiply like bases, we add the exponents. Also, can we take the square root of a to the fourth? It'd be a squared. So that is a perfect square, and 9 is 3 squared, or 3 times 3. So this is still the difference of perfect squares. So what would we get? A minus 3 times a squared plus 3, yes? Now we have to be careful with this case here. Because if I look at this one here, we do have two things being subtracted, yes? Is a squared a perfect square? Yeah, it's still a number times itself, or a term times itself. That's still a times a. Is 3 a perfect square? No. So we're done. If it had worked out that I actually had a squared minus like 4, that's still a difference of perfect squares, yes? So we could factor it further. So in some cases, if they threw this instead of, say, 9, not 36, say 16, there's a chance we'd have to take it further. And I have a feeling I did put one on here. So not this one, but the next one will fall into that category. And if they throw that on the ACT, factor it completely, because it has another difference of perfect squares, we would have to factor it again. It's not factored completely. But let's look at this one here. K to the fourth minus 36. K squared plus almost K squared minus that is 6 squared Now 6 is not a perfect square, so that's as far as we can take it. Now the k squared plus 6 is not a difference of perfect squares, so it doesn't factor. Or at least have real factors. Now the last one of this type that we're going to look at today is the x to the fourth minus 81. Okay, I might have added this in. I need to fix the note sheets then. X to the fourth minus 81. Okay, I definitely added this one in because I wanted one that worked this way. Now, here we can say that this is x squared and this is 9 squared, yes? So this would factor down to what? X squared minus 9 times x squared plus 9. So it's still following the same type properties of the difference of perfect squares, but instead of just having x like we did before or last semester, it's having x squared. But if we look at this one here, x squared minus 9, well, x squared and 9 are both still perfect squares. So this here would actually factor to x times plus 3. Now here, we're just going to keep this as x squared plus 9, because this won't have real factors. Is it factorable? Technically. Because this here would actually factor to x plus 3i times x minus 3i. And the way that we would get to that is really just taking it and setting it equal to 0 and solving. we would subtract 9 from both sides, saying that x squared is equal to negative 9. Taking the square root of both sides, telling us x is equal to plus or minus 3i. Splitting it into the two cases, saying that x is equal to 3i, x is equal to negative 3i. Essentially going backwards, getting them back equal to 0, x minus 3i, x plus 3i. So those are the factors. So really getting the imaginary parts or the imaginary factors really isn't a big concern. This here would be considered factored form. It is to get the complex versions of the factors or the irrational, the ones with the square roots, we would almost have to solve them and then merge them back into factored form. So this here, none of this in blue is really a big concern. This is completely factored. Because the only reason that they would expect it in plus or minus 3i is, well, if on the ACT they give it in that form or ask you for all the rational, be more specific, but this is completely factored, at least for my sake, or what I care for. Any questions on this here? All right. What we're delving into next, and the rest of this note sheet is completely new for y'all. It is completely new. Because we didn't have time in chapter 4, the last chapter we did before the break with higher degree polynomial functions, to actually delve into factoring. And on a whole, it does help somewhat, but it's not a huge critical thing. Because a lot of the stuff that we could do with factoring, well, we could actually solve in other ways. Now, the first one that we're going to look at is the sum and difference of perfect cubes. So if we have two numbers being added or subtracted and are perfect cubes, a number in term, or a term that can be multiplied by itself 3 times, then we can factor it in the following way. A plus b times a squared minus ab plus b squared, and a minus b times a squared plus ab plus b squared. We get it in this form. There is one thing that is guaranteed every single time. The quadratic part of this here, this factored form, will always be complex. It will always have complex solutions. So the only real part is going to be a plus b or a minus b. And it'll work out that way every single time. And this will make a little more sense as we get into it, okay? Any questions on this here so far? I'm going to shut the door for a minute. So if we look at this here, for any of these here, the signs are always going to be the same. Opposite always ended on a positive note. Now, for the rest of the terms and how this works out for this formula here, we're really going to find what the cubed form of both of these here. So if we take the cubed root of the first and second term, or the two terms, we plug it in as a and b. Here, in the quadratic form, it decreases in power. Because if we look at a squared, it goes a squared, a, and then it's gone. Because really, in this third spot, it's actually a to the 0. Because the power was 2, 1, 0. B is actually going in the opposite direction. Here we actually have b to the 0, then b to the first, and then b squared. Now, when we look at an actual example of this, it'll actually make a little more sense and work out a little smoother than what you think it might be. So let's look at the first example here. So we do have two numbers here, and it'd be good to see if they are perfect cubes. Well, x cubed is most likely going to be a perfect cube. So if we take the cubed root of x cubed, would be, well, just x, because the cubed root and the third power will cancel out. Now we need to see what the cubed root of 125 is. Well, it works out to be 5. And again, we can plug most of these into the calculator. We can't do the variables, but we can definitely take the cubed roots of the numbers to see if they work out to be whole numbers. So what that tells us is that this here is the sum of perfect cubes. So that means we can actually factor this using the sum of difference of perfect cubes. Now, for the parentheses, what we're going to create is something I call the tractor trailer. Because the first one has 3 spaces. The second one has 5. So it kind of looks like a tractor trailer to me. Now the signs for this here are going to be the same, opposite, always end on a positive note. So since the first one is plus, our first sign is going to be plus. The second sign is going to be negative, and then positive. Same, opposite, always ended on a positive note. And that especially will be helpful on the ACT, because I know that there's probably at least one on at least one of them or few that will ask you to factor these here. And even if you're not for sure if it does, or for sure it does factor, but just looking at the setup, well, same, opposite, always ended on a positive note. So you can look through the answer choices of it being factored and seeing which ones match up. If this was on it, well, any of them that don't have plus, minus, plus would not be the correct answer. So we can eliminate those to begin with. Any questions on this so far before we start plugging variables and numbers in? Okay. Let's start with x. Now x is going to be defined as a because it came first, so it's going to go first. So in the first part here, we're just going to have x. Inside the tractor trailer, well, we're going to have x squared, x to the first, and then the last one is going to be x to the 0. And anything to the 0 power actually just reduces to 1. So it won't show up. Any questions on this so far? Now we can take the other term, 5. So in the first set of parentheses, it's going to come in as 5. With the x squared, it's really 5 to the 0, so it's just 1, so we don't have to write that in. In the middle, we will have 5. And in the last one, we're going to have 5 squared. Now, it might seem a little silly to put x in parentheses squared because, well, that's the same as just x squared. But we want to do that just on the off chance that there is a number with x. Because if we had, say, 8x cubed, the square would affect it as well. Any questions on this here before we simplify down? Now, the first set of parentheses really isn't going to change. We're just going to have x plus 5. X squared is just x squared minus 5x. X times 5 is going to be 5x plus 25. And that's it. Easier than y'all thought that was going to be? And luckily it works out in that nice pattern and that nice flow for us to be able to get there. We ready for another one? X cubed minus 64. So we need to see if these are perfect cubes. Can we take the cubed root of x cubed? Well, yes, and we get x. Now we need to see if we can take the cubed root of x, or cubed root of 64 For the graphing calculators to find the cubed root, if we go math and then scroll down, it will actually give us the cubed root. Pull that up here. There it comes. Close. So on the graphing calculator, if we go math, and the fourth one down, this here is the cubed root. The one below it is really any other root we want to take. Helpful if I got out of that. So math, cubed root of 64. And it tells us that it is 4. So we can take the cubed root of 64, and it is 4. So that means that this here is the difference of perfect cubes. Now, if it doesn't work, that we can't take the cubed root of both of them, see if there's a perfect square, or not perfect square, a greatest common factor between the two terms. Because it could work out that there is a greatest common factor that we need to pull out first. Let's do the signs. So the signs are going to be the same. That's it. Always end on a positive note. Same, opposite, always end on a positive note. So since it was negative to begin with, we're going to go negative, positive, positive. Same, opposite, always end on a positive note. So it's going to work out for every single perfect, the sum or difference of perfect cubes, we will always have 2 addition signs in there. Either 2 in the bigger part, or 1 in the bigger, 1 in the smaller. We'll always have 2 pluses. Now let's plug in the first term. Well, that would be x, because x cubed came first. So here we would have x. Here we're going to have x squared, and here we will have x, and then the last one's technically x to the 0, but we don't have to put that in. For 4, we would have 4. Here is technically 4 to the 0. Then we would have 4 to the first and 4 squared. So this here actually factors down to x minus 4 times x squared plus 16. And we get this here. Any questions on any of this here? There we go. Let's look at this one here. I have a feeling that it's not, okay. It doesn't have the 27. I added that back in. I need to fix these note sheets. Because I realized, and I don't think that one shows up either. No. Yeah, when I created these, I realized that every single one of them had a cubed, or a variable cubed, and then a number. We didn't have anything in front of it. So I need to fix the note sheets and go add this back in. 27a to the 3rd. Now, the process that we do is the exact same, because we're still going to take the cubed root of both to see if they are perfect cubes. Now, unfortunately, in the graphing calculator and the yellow calculator, I can't actually type in the cubed root of 27a cubed, because both of them need a value for a. But what I can do is we can come over here and go math down to the cubed root and type in 27 and see if we can take the cubed root of 27, which is 3. So over here we know that the cubed root of 27 is 3, and the cubed root of a cubed would be a. We can do the cubed roots of the variables easier, or pretty easy. They're not too bad. Now the cubed root of 64 is 4. Yeah. Let's find the sign. So our signs would be the same, so positive, opposite, so negative, and because we always want to end it on a positive note. The same, opposite, always ended on a positive note. So here is plus, minus, plus. Now, since the 27a cubed started first, and the cubed root of it was 3a, it's going to go first. So in the first set of parentheses, we would have 3a. Here we're going to have 3a squared, 3a to the first, and then 3a to the 0, which would just be 1. Now for our next set of terms, we would have our 4. So here it would be 4, 4 to the 0, 4 to the first, and then 4 squared. Any questions on this so far? So this would simplify down to 3a plus 4 times, well, 3a squared would be 9a squared, because 3 squared would be 9 and a squared would be a squared, minus, well, 3a times 4 is 12a plus 16. And that there would be it factored completely. Any questions on this here? Now, I think there's a little space out to the side of that one, isn't there? Let's look at this one here. We'll finish up with this one here. We'll stop here for the day because I know we have about 10 minutes left. And we'll do the factoring by grouping. That's the last thing we'll look at with factoring tomorrow. Now, when we look at this here, we want to see if we can take the cubed root of both. Now, x cubed and y cubed, we can take the cubed root of. So really the main question is, can I take the cubed root of 192x cubed and take the cubed root of 81y cubed? So math down cubed, oh, is it 192? Math cubed root 81 okay. So let's look back at this here. Is there a number that can go into both of these here? Because 9 does work, but there is another number that's a little bit smaller that would work better. 3. Because if we factor out a 3, 192 becomes 64. Well, we've already showed that 64 is a perfect cube. And 9 actually won't go into 192, unfortunately. It will go into 81. Now, 81 divided by 3 is 7. And I think we've already shown 27y cubed is a perfect cube. Yes? So the cubed root of 64x to the third and the cubed root of 27y cubed is going to be 3y. So there is a chance that it would work, but we just have to pull out a greatest common factor. Now our signs would be the same, opposite always ended on a positive note. Then we would have 4x squared, and 4x. And for our other one, we would have 3y. In the middle, we would have 3y. And lastly, we would have 3y squared. And this here would simplify down to 3 times 4x minus 3y. Now 4x squared would be 15x squared plus 12, because 3 times 4 would be 12. And then we would just have xy plus 9y squared. And that would be that factor. Any other questions on this here? So we'll stop there for today.